Hello everyone. In this session, we will be discussing computer arithmetic in Unit 2, which talks about Booth's multiplication. So, the difficulty of a sequential multiplier is we cannot use it for multiplying negative numbers. So, to overcome that, we are using Booth's algorithm to multiply signed numbers, that is both positive and negative numbers. And the advantage of Booth's algorithm is when another advantage of sequential multiplier is when you have the number of ones in the multiplier, the number of additions will be equivalent to the number of ones in the multiplier. So to reduce the number of additions, we can use Booth's algorithm. So if you see the Booth's algorithm, the multiplier is recoded, Booth recoded, and when you have after recoding, you can see. So this is the normal multiplier where you can see 0, then followed by ones and then zeros, two zeros. So you have four ones. So since you have four ones here, you need to add four times. And our aim is to reduce the number of additions in the Booth's algorithm. So you can see how this multiplier is recoded in Booth. So this is the Booth recoding. So when you always assume that the right of the least significant bit is equal to 0. So 0 to 0, no change. So it depends on the positional changes of bits. So it is 0. When there is a change from 0 to 1, you recode it to -1. When 1 to 1, no change. So here it is 0. Again 1 to 1, 0, 1 to 1, 0. Now 1 to 0 is there. So you have 1. And then 0 to 0, so 0. So you can see the multiplier is recoded with a +1 and a -1. The number of ones is initially 4 and the number of ones here is 2. Now if you see, you need to just take the 2's complement of the multiplicand when it is -1 and add, and for this you have to take multiplicand and add. So two additions are only needed. So it's an improvement or reduced number of iterations and additions in Booth's algorithm. So here you can see how an example of how an multiplier is recoded, Booth recoding. So 0, 0, 0 to 1 -1, 1 to 1 0, 1 to 0 so +1, 0 to 1 -1, 1 to 0 so +1, 0 to 1 -1, 1 to 1 0, 1 to 1 0. Likewise you can go. So here is an example. 13 plus 13 multiplied by -6 plus 13 is represented as such, and -6 is recoded, and you can multiply and you can get the result. And it is not always Booth's algorithm works fine. For any random number, you can see a reduction of the number of ones. But if you have a sequence of ones, you will have very less number of recoded ones. And the worst case is if you have alternating zeros and ones, it actually increases the number of ones. So you go in for another method called bit pair recoding, where you group two bits of your binary Booth recoded number and convert it to a single number. So if you have first step is the multiplier is converted into a Booth recoding. Once it is converted into a Booth recoding, then you have to combine the two bits. So -1 is brought into the least significant bit, which will be -2. So if you remove the position right for one bit, then the weight increases by 2. So -1 becomes -2. So you add both the weights, it becomes -2. So here if you see, -1 becomes -2, -2 plus 1 becomes -1. So if you see all combinations of the Booth recoding, you will get either plus 1 minus 1 or plus 2 minus 2, or it will be 0. So if it is plus 1, you can add the multiplier as such. If it is minus 1, you have to take the 2's complement of the multiplicand and add. If it is plus 2, you have to do plus 2 into m, means it is shift left operation or a shift right operation, and if it is minus 2, it is the 2's complement which should be shifted. So the operations are less. So here you can see the booth recoded, and this in turn is bit pair recoded, and the number of partial products has been drastically reduced by half. So further we can improve the number of iterations in when we are adding the partial product by applying carry save addition. So by default, you do a ripple carry addition. So full adder will give the carry out to the next successive full adders of the same level. So this is the ripple carry addition we followed for adding your partial products. Now if we want to do a carry save, here the drawback is every full adder has to wait for the previous bit to complete. In order for a particular level to complete at the same time, you can make the full adders carry out output go to the next level, not to the same level. So in that case, you can have a faster multiplication. And if you have more number of bits, you can see. So here you have partial products of A to F. So you have A, B, C and D, E, F. Instead, in the previous carry save addition, you can give 3 partial products to one level of full adder. So ABC can be given to a full adder level, and it creates a sum and carry. Then here DEF can be given to another full adder level, and it can create sum and carry. Now these three can be given to another full adder level, so sum and carry, and this three can be given to another full adder, and you can give a sum and carry. So 1, 2, 3, 4, and finally 5. 5 levels will be needed to get the product. Instead of 1, 2, 3, 4, 5, and 6 levels, you have reduced the number of levels. So this method you call it as carry save addition of summons. So in by booth bit first step we did booth recoding, second we did bit pair recoding, and after bit pair recoding we also implemented carry save. Instead of ripple carry, we had carry save addition of summons, which in turn reduced the number of partial product additions. Thank you.